Now let's have one example. How can we compute the variance? Let's compute the variance of binomial, right? We already computed that, and let's compute the variance of binomial. So let xi has binomial distribution with parameters n and p, right? Then variance of xi is given by the expected value of xi squared minus the expected value of xi, and the whole thing is squared. From here, we already know what? We already know the expected value of xi, which is equal to what? NP, right? So this is equal to NP. We don't know the expected value of xi squared. And let me write something by the way. This is some notation. We call the expected value of xi to the power k. This is called the kth moment of xi. This is just the name, okay, the kth moment. So here we have the second moment of xi. We just need to compute the second moment of xi. How can we compute the second moment of xi? So let's do that right here. Expected value of xi squared. So what is the formula that we need? The PMF, yeah. So we need the PMF, but so we need a sum, right? We need a sum over all the possible values of xi, which are all naturals from 0 to n. And then here, what do I need to write over here? So here we had k for the expected value without the square, right? So without the square, we had here k. So here we need k squared. Why can we do that? Can we? We can do that. There's one property that allows us to do that, right? Property number 4, 5 that we had today. So that the expected value of a function of xi is equal to the sum, and here we'll have phi of k by the probability that xi equals k, right? So this phi of x, so here we have written actually phi of xi, where phi of x equals x squared. So we have the expected value of a function of the random variable xi. The function that we have is x squared. This function is a Borel function because it's continuous. So we can apply the property that we have, and then here we'll have just phi of k, so k squared, by the probability that xi equals k. So all that we have to do now is to compute this sum, right? So let's do it. So look, we already compute the sum when we didn't have this square, but we had only k. What was the answer? The answer was like this, was NP, and we had the sum from J0 to M, and now let me write this K. So here we will have this extra K that we didn't have before, right? But K is, so K minus 1 is equal to J, so K is equal to J plus 1. So here I will have J plus 1, multiply this by, we had M choose J, P to the power J, 1 minus P to the power M minus J. Yes? So I skipped everything that we already did for the computer, for the expected value, right? The only difference is that here we have this K, because here we have K squared. Before we had only K, all right? And K is equal to J plus 1. Now I'm going to divide this sum into two sums, the one with J and the other one with 1, right? So I will have NP, and I open these brackets. I will have the sum from J0 to M of J multiplied by this whole thing. Let me write this. Let me call this just, I don't know, M, capital M, right? Just like this. Okay? Plus the sum from J0 to M of capital M. Yeah? So what is this equal to? This is equal to 1, right? This is equal to 1. And what is this equal to? No. So we already solved this at the beginning. Look, what do we have here? We have the sum from 0 to m of j, from 0 to m, of j multiplied by this. This is the probability that psi equals j, where psi is a random variable with which distribution? So this is equal to the expected value of binomial distribution with parameters MP. Now MP. So M is the number of trials and P is the probability of success. So this is exactly the same that we had for the expected value right here. The difference is that now we don't have K, we have J. We don't have M, we have N. Sorry, we don't have N, we have M. Right? So you can write here K and here this with N choose K. And you have exactly the same. We already proved that. So this is the expected value of this. We already found the expected value for this. The expected value for this is going to be MP. Right? So the whole thing is equal to NP. Here we'll have MP. M is equal to N minus 1. So this will be N minus 1 multiplied by P plus 1. This one is this one from here. So we can go back to the variance. We can replace this and we can find the variance. So let's do it. So this is NP. So NP squared minus NP squared plus NP minus NP squared. So this is equal to N multiplied by P by 1 minus P. And this is the variance of binomial distribution with parameters N and P. NP by 1 minus P. Yes?
Okay, would this mean that variance for Bernoulli distribution would just be P by 1 minus P?
Again, please?
The variance using Bernoulli distribution would just be P multiplied by 1 minus P. Because
which distribution? I don't know.
Bernoulli, because by
Bernoulli, yes.
Yeah, so just take away
Well, not from here, but so we need to find for Bernoulli. Bernoulli will be P multiplied by 1 minus P, and then N times that we'll have this. Yes, but only because, well, we don't know that yet, actually, because here we don't have the variance of the sum. So for the expected value, we had that the expected value of the sum is equal to the sum of their expected values. But here we don't have it. So we will have it right now.